This is another classic alkene reaction that I personally think kind of just gets glossed over because there's one, just better ways of making alcohols, and two, the reaction mechanism is very similar to the HBr. It's essentially the same to the HBr reaction mechanisms. You're not realistically being taught a new reaction mechanism. So it gets just brought up briefly and then kind of glossed over, but it's important nonetheless because it is a reaction. So as you'll note here, we have catalytic acid. Actually, sorry, before I say it, this is known as the hydration of an alkene. We take an alkene, we add water across the bond, we create an alcohol at the more substituted position. This is Markovnikov addition. Now, all right, back to our thing. As you see here, it says H plus, comma, H2O. Now, this isn't just acid. This is catalytic amount of acid. That's generally what that means when you see this type of notation. We're just generically referring to catalytic acid, whereas overwhelmingly more water. And usually use a strong acid, typically sulfuric acid, H2SO4, or phosphoric acid, H2PO4. And you might be thinking to yourself, that just seems like the same reaction conditions for dehydration of an alcohol, but backwards. And you'd be exactly correct. These are complementary reactions where the dehydration of the alcohol, the reaction error is going this way, the hydration, the reaction error is going this way. And that is why I said we only have catalytic amount of acid, because we want there to be an overwhelming amount of water molecules for every free proton. And that's why, remember, when you see dehydration of an alcohol, usually it'll say concentrated sulfuric acid. So let's walk through our mechanism here. What's going to happen? Our pi electrons in our double bond are going to come and grab that proton. And we're going to form a carbocation at the secondary position. And this is why I say this is the same reaction mechanism as HBr addition, because this is what it looks like for HBr addition. Now we have water. It's going to come in and nucleophilically attack that position. And we are going to have H2O plus. And we're going to have another water molecule, because remember, there's an overwhelming amount of water in here. It's going to come and steal that proton. We're going to kick those electrons up there. And it's going to give us our alcohol. And then we also regenerated our acid catalyst to make H3O plus, which is roughly equivalent for this case to a proton plus H2O. And we've generated our acid catalyst. Now, as you notice, like I said, this is Markovnikov addition at the most substituted position, and that is because it proceeds through a carbocation mechanism. Remember, carbocations are most stable at the most substituted position. Now, because it proceeds through a carbocation mechanism, that also means if there is a rearrangement that can happen, it likely will happen. So let's work through an example right there where we have a rearrangement happen. This is something you need to keep in mind. Remember, whenever there is a carbocation mechanism, you need to be wary of a rearrangement. So say we have this, but now instead of this being another primary, now there's a tertiary spot, okay? Say we have H2SO4, and then H2O, excess. So we have excess water. What are we going to do? We're going to protonate this position. I'm just going to say we're going to steal one of those protons. We're going to form this carbocation right here, or our protons right there. Now, what do we say? Carbocations are more stable at more substituted positions. Well, it's at a secondary, it's more stable than this primary. We have a tertiary right here. So we're going to undergo a hydride shift, which is a type of carbocation rearrangement, where a proton moves. I'm going to get it more specifically to that carbon. And that's going to give us a tertiary carbocation. Because now this is the more stable carbocation. We have our protons right here. Now we have water attack, and we form our H2O plus. We have another water come in. We're going to steal the proton. Sorry, I'm running out of space a little bit here. Pick those electrons up, and we form our alcohol. Now, as we can see here, this alcohol didn't add at this more substituted position like we wanted, because this proceeds through a carbocation mechanism. And I think this is another reason why this reaction mechanism isn't really taught that much, because there's much better ways of creating alcohols and making sure they stay exactly where you want them to stay. Specifically, we're talking about something like this. You would use hydroboration or oxymercuration to create an alcohol where there's no carbocation mechanism involved. There's no chance of a rearrangement. However, this is still a good reaction to know, and you should, because it exists. If you want to get more organic chemistry learning, be sure to hit that follow button.